So in this problem, what are they saying? The variable resistor in the circuit figure is adjusted for maximum power transfer to R0. So what does it mean for maximum power transfer? It can be proven, we won't try to prove it, that for this circuit to produce maximum, not for the circuit, for this resistor to give a maximum power, for the power here to be maximum, it implies that the resistance value here, R0, must be equal to the Thevenin's equivalent resistance, R Thevenin. So, in other words, we have to first determine what the Thevenin's resistance is for the whole circuit when we consider this variable resistor as the load resistor. Once we can find the Thevenin's equivalent resistance, then to get maximum power transfer, this R0 must be the same as that Thevenin's equivalent resistor. So that is the first thing that we have to do. So let's proceed to get the Thevenin's equivalent resistance for our circuit with R0, the variable resistor, as the load resistor. Okay, so we've just pointed out that to get maximum power transfer to RO there, that it implies that the resistance R through R0 must be equal to the Thevenin's equivalent resistance. So if we take the variable resistor there as the load, let's find the Thevenin's equivalent resistance. So to get the Thevenin's equivalent resistance, we first open the load. So we'll remove the load from our circuit. So copy the circuit and then just omit the load from there. So remove the load. With the load out of the way, now we have this circuit. So we now want to find the total resistance viewed from where the load was. So with something like this, how do we get the total resistance? Remember how it goes? If you have a voltage source, short it. So you have a voltage source here, short it. Next, if you have a current source, open it. So you have a current source there, open it. So the circuit reduces to this. Now for this circuit, what will be the total resistance viewed from where the load was? So this is what we're trying to solve. Well, in this case, these two are parallel to each other. So we have the 24 parallel to the 48. Next, once those are combined into one, notice that they will be in series with these two. So you can say plus 1.6 plus 1.8. But first, let's get what this is going to be. So here we get 16. Then we have plus 1.6 plus 1.8. So we add those, we get 19.4 kilo ohms. So far, if we get our circuit to just show you how far it has been reduced. We first combined these two and they reduced to just one resistor, and that resistor was a 16 kilo ohm resistor. After that, we saw to say that now the 16 kilo ohm resistor, the 1.6 and the 1.8 ended up being in series. So we added them to get 19.4. So we now added these and the circuit reduced. So that now this side we have 19.4 kilo ohms. Now notice that the 19 and the 5 are now in parallel. So that we can now say that our Thevenin's equivalent resistance will be 19.4 by 5 over 19.4 plus 5. So we get 3.975 kilo ohms. So this becomes our Thevenin's equivalent resistance. And remember, for maximum power transfer, R naught, the variable resistor, must be equal to the Thevenin's equivalent resistance, which is 3.975 kilo ohms. So this is what R naught must be for us to have maximum power transfer. In the second part of the problem, they're saying find the maximum power that can be delivered to R0. Now they actually want the maximum power itself. What is the maximum power that can be transferred that can be delivered to R0? So we already have the value of R0 that allows for maximum power to be transferred. But now what is the actual power, the actual maximum power that can be transferred? To get power in a circuit, we need current and voltage. So voltage times current. We need these two. If not this way, then we can use voltage is equals to IR to change this expression so that where there is V, we can put IR. And this expression changes to I squared multiplying by R. We already know what R is for maximum power, but what will be the current I? So we see that we must then find the current that will pass through the load resistor. Once we get that current, we can use it in this expression to get what the maximum power is going to be. So that is what we now need to do. But how do we do that? Well, to find the current that passes through that point, notice that now we can use any approach that we are comfortable with. But seeing that we have already found the Thevenin's equivalent resistance, we might as well use the Thevenin's method of getting the current there. So in other words, I will reduce this circuit to a Thevenin's equivalent circuit. So I have already found in Thevenin's method, we have already found the Thevenin's equivalent resistance, R Thevenin. Now we just want to find the Thevenin's equivalent voltage, V Thevenin. If we can get these two, connect them to our load here, R0, it will be easy for us to get what the current passing there is going to be. So we can take it this way, or if we want, we can still use the Norton's approach. Either method is better, so whichever method you want, you can go with that one. If we use Norton's theorem, then instead of looking for V Thevenin, we'll be looking for I Norton. If we're using Norton's current, then we'll be finding the Norton's equivalent circuit. The best thing about these two is the equivalent resistance will still be the same. The difference is that now in Norton's theorem, the resistance will be here. But it will still be the same resistance, R Thevenin. I can present it as R Norton now, but they have the same magnitude. And then here, we'll still have R0. Now this will be I Norton. So whichever is easiest for you to pursue, you can follow that one. But ideally, they will all give the same current through R naught there. They all give I. Let me label it as I0. Okay. So which method is easy to use? Right. So to work out this problem, as I pointed out, we can use Thevenin, we can use Norton's theorem, we can even use source transformation here. We can easily get the current that will come this side as I0. But for this approach, we're going to choose to use Norton's theorem. We're going to choose to use Norton's theorem. But what happens when you try to use Norton's theorem here? So in Norton's theorem, first thing that you do is you have to find the I short circuit. So short your load. Here the load is the variable resistor here, so remove it and then we'll short it. So when the load is shorted, what will be the I short circuit? So the current that will be passing here will be the I short circuit. The I short circuit will be equals to the I Norton. So what does a short circuit in a circuit like this change? Well, it changes one thing. When current is coming this way, as it reaches this junction, it sees two routes. One route goes through the short circuit. The other route comes to pass through the 5 kilo ohm resistor. Now, current will always take the easiest route here. So one route has a resistor. The other route does not have a resistor at all. So in this case, current will take the route with no resistance. If you want, you can even try to use current division here to determine the current that will go towards the 5. If I label that current as I, and the current that they are sharing, let's say I from the source, from the supply, then notice that I towards the 5 kilo ohms will be the other resistor. But look at this. This line has no resistance. So it will be 0 on top over the sum of the resistance 0 plus 5, multiplying the current from the supply. Notice that the current that will go towards the 5 kilo ohms will be 0. No current goes there. So as long as you have a short circuit in play parallel to a component like this one, no current will go towards the component. If this was a bulb, this bulb will be off because all the current will bypass it going that way. So with that in mind, we can see that for this circuit, with the short circuit in play, it will be as if the 5 kilo ohms is not even there. So let's redraw the circuit so that we show how it will now look like. So as I pointed out, if the 5 kilo was a bulb, it will act as if it's not even there. The circuit will basically behave like this. So this is currently what we have. You see, I wanted to also switch off, say that the 48 kilo ohm will act similar to the 5 kilo ohm, but it is not parallel to the short circuit. What makes it not to be parallel, it's this resistor here. So if this resistor was not there, then the 48 kilo ohms would have also been shorted by the short circuit. But because of the 1.6 kilo ohms, the 48 survives. It will still be part of the circuit. So basically, this is what we have. So for this circuit now, we want to find the current that goes towards this end. How do we do that? So for this circuit, to understand what I Norton there is going to be, we can source transform this part to understand so that we get how much current. We express it in terms of current and resistance. So as a current source, this is going to be the voltage, 60 volts, divided by 24 kilo ohms. So that's key 24, not 2.4. Let me just confirm. I think that's 24. Let me just verify from the original problem. 24. Okay. Okay, so here we get 2.4. All right, so this is 2.4, not 24. Yeah, 25. So 2.4. So here we get 25. But remember, this was in kilo ohms, so this will be in milliamps. Or it will have times 10 to the power negative 3. So when the circuit is redrawn, after source transforming, what changes? So notice that our I short circuit remains the same, but this part here changes so that now we have a resistor connected parallel to a current source. current source will be 225 milliamps, and then the resistance will still be 2.4. Okay, so now this is what we have. You see, this becomes easy for us to evaluate. Let's see. These two can be combined into one resistor. So those two can be combined. They are currently parallel. So since they're parallel, combined parallel, we just say 2.4 by 4. Yeah, I think when we started, but we used 24 and 48. I wondered why these were big. So these are supposed to be points. This is supposed to be 2.4, 4.8, 2.4, 4.8. Answer when you do it like this now. What would be this? So this would be 1.6 instead. Yeah, so one thing we're learning here is to be very careful with how we present things, otherwise you can end up confusing yourself in the process. I think just the way I wrote them, I wasn't seeing the point afterwards. So now when we add 1.6 and 1.6, get 2.8, 2.8 plus 1 point. We get what? 5? Okay, yes, so here the final answer becomes 5 kilo ohms. Okay, so this becomes our final R0, our Thevenin's value. So that would be 5. Okay, so yes, R0 becomes equals to 5. Okay, so having obtained R0, everything else here I think was okay. We're getting we use 19 here again. Okay, so here we use 19. No, this was not R0, this was just a combination to get 5 kilo. So 5 kilo now. Pardon?
Let's just check through how we got this 19.
It was here. First, we combined these two to get 16. Now we've done it correctly to get 1.6. Then added 1.6 with this and this, since they're in series, to get 5.5 kilo. 5 kilo is the one which was 19 here. So this is not 19, this is 5 kilo. Now we're seeing that this combines to 5 kilo, but it will now be in parallel with another 5 kilo here. So that now we have 5 kilo in parallel. So remember, when they have the same resistance, they always reduce to half of 1. So it will be 5 by 5, 5 plus 5, 2.5. Have you seen that?
Yes.
Okay. So this becomes the overall Thevenin's resistance, implying that even our R0 will be equal to that, 2.5 kilo ohms. Okay. So that was the first part. Now, for the continuation here, let's write them properly. So that's 4.8, 2.4. No, 2.5 again. 2.4. 4.8. Okay, so now here, everything else we did here was okay. It's where I want to start using them. So here we use the correct 2.4. We got 25 milliamps. Now here we're trying to combine the 2.4 and the 4.8 here. So here we have 4.8. Since they are parallel, we're doing it this way, 2.4 plus 4.8. So what will be the combination here? So we get 1.6 kilo ohms. So what this implies is our circuit would be the same as these two seen as one, as just 1.6. Okay, so this is basically what we have. Now, these three elements are in parallel. Order does not matter, so we can change the order so that now we present them as we have 25 milliamps here. Then here we have 15 milliamps. And then here we have the 1.6 kilo ohms. Then here 1.6 kilo ohms. Then here 1.8 kilo ohms. The one that comes here is our I short circuit. These two can be combined. One is feeding up positive, one is feeding down negative. So when you subtract, we get 10 milliamps. So in other words, these two can be combined to just 10 milliamps. So in place of these two, you can just put a 10 milliamp supply up. Now we want to get I short circuit after reducing this to just one current source. Getting I short circuit becomes easy. There is no need for us to combine them because we are interested in understanding the current that will pass through there, which is the current that will pass through the 6 and the 1.8. So if I label this current as I, then I here, basically that's I short circuit, so just take it as I short circuit. I short circuit will now be equal to, since the two, the 1.6 and the 1.8, 1.6 plus 1.8, they're in series. So we'll look at them as a sum like that. Since they are together parallel to the 1.6, to get what I short circuit will be, we'll use current division. In current division, it's the other resistor, 1.6, meaning this one here, divided by the sum, the 1.6, this one again, plus the other is this one here, the resistor which is here. And that resistor is a combination of 1.6 plus 1.8. Then multiplying the current they are sharing. These are sharing 10 milliamps. So it will reduce to that 1.6 over 1.6 plus 3.4, multiplying 10 milliamps. Then what will be the final solution here? So here we get 3.2 milliamps as our I short circuit. What does that imply? Our I short circuit has come out as 3.2. Remember, our I short circuit was the same as our I Norton. And since we now have our I Norton, we can go back to Norton's circuit. So we can now create our Norton circuit. So for this circuit, I Norton 3.2 milliamps. R Norton, we already found the Thevenin's resistance when we started. It was 2.5 kilo ohms. Yes, 2.5 kilo ohms. So that comes here. and then R Norton or R the load resistor there. Remember, for maximum power transfer, the load resistor must be the same as the Thevenin's equivalent resistance. It must also be 2.5 kilo ohms. Now, in this way, we can now easily find what R naught has to be. And guess what? Because these are the same, when we use current division here, they will share this current equally. So the current I0 here will just be equal to half of 3.2. So it will be equal to 1.6 milliamps because they will share equally. Once we get the current I0, we can now get power. The power developed by the load there, we already substitute to be I squared multiplying R. So this is going to be, I don't want to use milliamps, so I'll use amps instead. So I use 1.6 by 10 to the power 3 minus 3 amps squared multiplying the resistance. I won't use kilo ohms, I'll use ohms. 2.5 by 10 to the power 3 ohms. Here we end up with 6.4 times 10 to the power negative 3 watts, or 6.4 milliwatts as the power delivered to the maximum power delivered to R0.